Okay, hi everyone. So I want to talk about a new perspective on matrices, which is the transformation perspective. So the idea is that we can reinterpret a linear system as a function. I guess I should say slash matrix as a sort of quote function, or there's these other terms that we're going to introduce, map. So another term is it's called a map, or another term is a transformation. I'll explain this. I'll give an example first to explain this. So let's look at an example. Let's say we have this 2x2 system, 5x1 plus 3x2 equals y1, and 3x1 plus 2y2. I keep doing the same y. X2 equals y2. So what I'm doing here is I'm first notice that after the equal sign, I'm using variables instead of numbers. But I want to, so that's the first thing, is to actually put, and we've done this a lot already, sort of where we've put we've changed the numbers after the equal sign, or sort of talked about the coefficient versus augmented matrix, or talked about a general augmented column. So this shouldn't be so out of left field, but I'll just say we can rewrite this as AX equals Y, where A is the 2x2 matrix with columns 5, 3, and 3, 2. And X is the vector X1, X2, and Y is the vector Y1, Y2, right? And I guess what I want to say here is that we can think of this as like inputs and outputs, like you would like a function where you're like the squaring function or something, and where you're like putting in a number, and then that's your input, and then your output is the square of that number. So we're doing the same thing here. Each choice of a vector, you know, the pair x1, x2, this is a sort of the quote unquote input, gives a value for y, the vector y. And that's like the output. Just for example, let's just say x is the vector -2, 7, right? Then what's y1? We're going to plug in -2 for x1, 7 for x2, and we get, I don't know, 11. And then y2, we plug in -2 for x1 again, and 7 for x2 again. 14 minus 6 is 8. So the output, so if we input the vector -2, 7, we get out the vector 11, 8. Right? It's like a function. Like a y equals f of x that we've seen before, except instead of having one number go in and one number go out, there's actually two numbers going in and two numbers coming out. So, but with two input variables and two output variables. By the way, you've also seen more than one input variable before in multivariable calculus. You looked at functions of 2 variables and 3 variables or more. But now the output can also have more than one variable. Okay, so here, if we want to think of it like a function, we would say something like, if we plug in the vector -2, 7, we get out the vector 11, 8, right? Okay, so that's the idea, is we're going to think of this as a function, and that's going to turn out to be a very useful way to think about matrices and about systems, that it somehow gives you a function. But I want to pause before I delve deeper into some of these examples and actually talk about some terminology, some notation, because there's all this language in mathematics that is very standard, and I just want you guys to know it so that it doesn't look too weird to you. So let's think about this. So you're used to functions like, let me just say it this way. You're used to functions, like I mentioned the squaring function before. Like say, f of x equals x squared. And we can say that's equal to y, maybe just to think about the input and the output variable. But the idea is that this notion generalizes, this notion of inputs and outputs generalizes to like almost any sort of ruler relationship in math. So it generalizes widely. That's the first point I want to make. To almost any sort of relationship or rule. Like the idea of a function. And let me explain that, or give some examples, maybe I should say, like, and by I mean you have some input that you put into some sort of like function and it changes it and gives you some output. So let me just give you an example. So like say you input a specific car, just to see how this doesn't have to just be numbers, right? Like a car, I mean, I guess you could identify it by like a VIN number, maybe, vehicle ID number. And the output, you could then output its color. So that's like a function on the set of all cars, right? So like I'm gonna plug every car into this, it's gonna output the color of the car. Or you could input a person. And then you could output their date of birth or something like that. So that's also like a function on the set of all people. And the output of the function is a number, and encoded somehow a birth date. Right. So this is what I mean by a map or a transformation. These things are called maps. It's a generalization of the notion of a function, but in higher math, people call them maps. So these are called maps, or maybe transformations, where you're taking one set, you think of it as a set of data or something, and you're transforming it into a different set of information. Like, and of course you might lose information, like taking the set of all cars and changing it to the set of all colors of cars. Certainly lots of cars have the same color, so you might be losing information sometimes, but it's still something that, it's almost like it gives you a window or a perspective onto some set of data. So these are called maps or transformations. And I'll just say that like most modern mathematics, is written in the language of sets and maps between sets. Let me give you the notation. Oh my God, that's really ugly handwriting. That says maps between sets. Okay, written in the language of sets and maps between sets. This is really what a lot of modern mathematics is. So let me just show you the notation that we tend to use. So if f is a function map slash map. I'm just going to use these words kind of interchangeably. With input set A and output set B, we write, the typical thing we write is something like this: F A to B, or maybe like F colon A arrow B, or maybe we just write the F on top of the arrow. Okay, and there's names for this. A is called the domain, which you've seen before, I'm sure, in pre-calc or something. The input, the set of all possible inputs to a function is called its domain. The domain of F. B is called the codomain. It's just another word, domain and codomain. Another word I could write more cleanly. Right, so let me just give you some examples, just to illustrate this. So examples we've been talking about. We could have the function f from the real numbers to the real numbers. That's kind of how you read that, given by f of x equals x squared, right? That's the squaring function. But inputs are real numbers and the outputs are real numbers, and you can input any real number, so that's why the domain is all of the real numbers. You could have the set P, the function P from the set of all cars to the set of all colors, right? Given by P of a car equals its color. You could have, just to keep using these examples I've had before, the set of all people to the set of all dates, given by, I guess I'm using B for birth and I was using P maybe for paint, above the B of a person equals their birth date. Let me just give you another example, because I sort of claimed all of modern mathematics is in this language. Let me just give you another example just to sort of show you. It's kind of silly, but we can think of a map from R2 to R. So you have two inputs, X and Y, and the output is their sum. So this is addition. Like, addition can be thought of as a map from the set of pairs of real numbers to the set of real numbers. And you can actually like state kind of everything in math in terms of like maps, like I'm saying, like even stuff about addition and multiplication and like the associative law and distributive law. You can state all this in terms of maps. It gets a little bit unwieldy, which is why we don't tend to do it in general, but it's possible. Okay, now the other thing I want to talk about just before sort of ending this video or going back to that first example is that I want you to note something. This word codomain I used for the set of possible outputs, that is not the same as range. You've probably heard the word range before for the outputs of a function. But let me just say it this way. Codomain, it's kind of like before you even start thinking about a function, even just to even define a function at all, you have to say what kind of things are output. Like, are they real numbers? Are they colors? Are the outputs dates? Are they, bananas? I don't know. So you have to sort of say what they are. So the codomain is sort of the type of thing the output is, to say it very poorly, is the type of thing output by the map or the function. Whereas the range is the actual set of all possible outputs. And I'll give an example which will illustrate this. The actual specific set of the outputs. And let me give an example just to make this clear. But this idea of range is going to be important, or there's another word actually we're going to use for it. But let's see what the squaring example, right? It's sort of like if you just define this function of like, I'm just going to square numbers, multiply them by themselves. I'm clearly going to get numbers out of it, right? So the codomain is the real numbers. But the range, if you think about, so it's almost like you have to analyze the function a little bit. If you think about the range, right? Like what kind of numbers are output by the squaring function? Well, you never get a negative number. So in fact, it's the real numbers such that y is greater than or equal to 0. That's what the range is, right? So notice it's different. And by the way, sometimes people would write this as something like r and then subscript greater than or equal to 0. But just notice the difference, right? The codomain is sort of like before you even think about what the function's doing, you just have to say, well, it's going to output something, and that's something to be a real number. That's the codomain. But when you start actually thinking about this, what the function's actually doing, you could say, oh, well, actually, it only outputs non-negative numbers. It never outputs a negative number. It could output 0 because 0 squared 0. It could output positive numbers, but and so that's the distinction between codomain and range. I just want to make that clear because it's going to be really important. And maybe one last note here is that there's actually a more modern term than range. So we actually use the word image. Or the term image instead of range. That's sort of the modern, again, the more, I mean, maybe you talk about range of a function, but like image could be just like of any sort of map, the image of a map. So that's a terminology thing there that we tend to use, image. And we can give it a pretty specific, I can give you the definition, right? Like if we want to really formalize it. So for f, again, the domain from A to B, some function f mapping A to B, domain A, codomain B, we can define the image of f like very explicitly. Define the image of f as, sometimes we just write lowercase im of f equals, it equals the following set. It's the set of things living in B such that y equals f of x for some choice of x in A. Right, that's sort of the set definition. Basically, there exists some x. It's a set of y's that get hit by the map, right? So that's kind of the formal definition. All right, now back to, okay, so that's kind of the really general like stuff that's used in all of math that you would learn when you take like a math reasoning class. But I want to go back just to finish this off to linear algebra specifically, because that's what we're doing. So in linear algebra, the domains and ranges, or domains and codomains, I have to be careful. The domains, the codomains are really Rn, right? In-dimensional space, I guess, or Rm, you could also say. Or later, there's this more abstract sense of something that's called a vector space. So we'll talk about abstract vector spaces. Usually capital V or capital W or something like that is used for a vector space. And the maps are called linear transformations. So we use these maps defined by linear functions, right? We just take linear functions of the input variables. And that's what we're working with here. These things called linear transformations. I mean, you can make more complicated maps, from R3 to R7 or something and have complicated functions, but we're just looking at linear functions of the variables. And we usually write or I'm going to write, we usually use the letter T instead of F, F for function, but we usually use y equals capital T of X. And, so T instead of F. So we're going to have maps T. If we're going to give them by n matrices, we're actually going to have, they're going to go from Rn to Rm. Okay, so back to our example from the beginning, just to finish this off. Before I took this long diversion into all this terminology, is the following. It was T of x1, x2. That vector is the vector 5x1 plus 3x2, 3x1 plus 2x2. We call that y1, y2. And so really what that is, or we could write that as the map T maps, notice the inputs are two-dimensional vectors and the outputs are two-dimensional vectors. So this is actually a map from R2 to R2. And it's given by T of X is AX, and that's equal to the Y, I guess, the Y vector, where A is this matrix. Blue 5, 3, 3, 2. And this is what we're going to be interested in is transformations given by multiplying by a matrix. Those are what linear transformations are. Okay, I've said enough. I'll stop there.